Hi, I'd like to talk briefly about precision, and specifically how can we demonstrate our understanding of the limitations of spatial data, both accuracy and scale generalizations, as well as our understanding of spatial analyses. And I'm talking about the slight erosion or degradation of precision that happens when we process data through a progression of analysis steps, and how spatial analyses and spatial data can affect the amount of precision that we can report our results with. So there are three basic types of precision that I'd like to discuss. The first is precision limited by data's accuracy. The second is precision limited by the data's scale. And the last one is precision limited by the processing or the analysis that we do. So let's start out in ARC. And if I can get this thing to cooperate with me a little bit. It's refusing. There we go. Okay, so this is a LiDAR digital elevation model of the Bear River in northern Utah. And I'm going to use the Identify tool and just click to identify the elevations as I go up the slope here. And so just take a look at this value. This is demonstrating that we have a range of values in this data set that ranges from 1,292 meters up to 1,706 or 7 meters. And I'm going to sample from the channel at 1302, 1318, 1351, 1407 as I go up the hill. Okay, so that's great, and with LiDAR we can get incredible precision on our values, our cell values. The problem is that data has accuracy limitations, and if you were to look at the metadata for a LiDAR data set like this, a typical vertical accuracy, so the accuracy of those elevation values, is often in the centimeter range. It might be between 8 and 9 centimeters. So what does that mean for our values? Well, it means that we need to question or be suspicious of the amount of precision that ArcMap gives us. In the table of contents, it's already giving us 2 decimal places. So this is precise to the nearest centimeter. And that might be an appropriate precision for this data. But this is precise to the nearest centimeter, millimeter, thousandths, to the nearest thousandths of a millimeter. That is not precision that's supported by the data's accuracy. Okay, we have 9 centimeter vertical accuracy. You cannot report elevations to the nearest thousandths of a millimeter. I hope that makes sense. So this is an example of accuracy limiting the amount of precision that we can report in our values. The second type of precision I want to talk about is limited by scale. So let me activate this data frame. This is the island of Maui. And this is a polyline mapping the major roads on the island. It was mapped at a scale of 1 to 100,000. This is a classic, map standard here. And if we pan out to the coast, there's a road that roughly follows the coastline. It's called the Hana Highway. For those of you who haven't been there, it doesn't look anything like this in reality. So what I want to discuss here is the idea of map accuracy and the map accuracy standards. And let me see if I can get this guy to cooperate. The national map accuracy standards mean that 90% of tested points of any kind of point line or polygon data set must be within 1/50th of an inch of their true location. And so let's break that down. 1/50th of an inch is 0.02 inches. At 1 to 24,000 scale, we can determine our accuracy by multiplying it out like this. Multiplying 24,000 by the 1/50th of an inch, we get 480 inches. Divided by 12 inches to a foot, we get an accuracy of 40 feet. Let's take it another step and go even coarser. At 1 to 100,000 scale, which is the scale of our road polyline, if we multiply that out, we get an error, an accuracy standard of 167 feet. So what does that actually mean? It means that when we see a location on a map, we're seeing its probable location, not its actual location. And the probable location is defined by this margin of error. So if we have a point that's been digitized at 1 to 100,000 scale, the actual location of that point, 90% of the time, needs to be within 167 feet of that actual point on the map. So how do we apply that to the idea of our polyline over here? If this was digitized at the scale of 1 to 100,000, at any given location on the line, it needs to be found within 167 feet of its actual location on Earth. That's pretty coarse. What I did is went in and digitized at 1 to 10,000 scale the actual highway, just for this small section. Let me zoom into that. So the actual Hana Highway is an incredibly sinuous, ridiculously fabulous road that runs along the north shore of Maui. And you can see here the difference in accuracy and precision that these two lines were digitized at. Mine still isn't exactly accurate. I digitized it, like I said, at 1 to 10,000, meaning it should be within probably 30 feet of its actual location or something around there. But you can see here is the road, and I don't hit it all the way. So if I were to ask you to calculate the length of a polyline like this, what's a reasonable number of significant digits that you can describe the length of this road using? And I guess, we can use the map standards to give us a ballpark, but I can't honestly say that there is a right answer. We're using a non-dimensional polyline to measure the length of something that's not straight, so we've got curves, that does have actual width. And so, can this polyline tack directly onto the center line of the road? And then could we get something that's sub-meter in precision? Perhaps. But even if a center line were to follow or a polyline were to follow the center of the road, it's very unrealistic to think that we could get sub-meter accuracy or precision on that polyline. And so I think the moral of the story here is to consider the scale at which your data was created and what it's actually representing. What kind of entity is it representing? So that's kind of the take-home message there. Now I want to switch gears to another example of how scale can impact our results, and then I'll talk about the processing last. So this is a hillshade created from a 10-meter elevation model mapping Cache County in northern Utah. And from that, I actually created, from a 30-meter data set, a 30-meter raster, I created a slope model. So if I zoom in on this and turn off the hillshade, we can zoom in to the point where we start to see individual cells. These are 30-meter cells, 30 meters on a side, mapped on the ground. It's pretty coarse. And when I turn the hillshade on, you can see that there's misalignment between them because the hillshade was mapped at a 10-meter resolution. So not the smartest idea to overlay those two. But there we go. So the idea is we've got this slope raster mapped at 30-meter resolution. What if I wanted to isolate, because I needed to build something and needed specifically slopes that were 5 to 8 degrees? These are the different raster cells in this extent that are between 5 and 8 degrees steep. Now remember, slope is calculated from a digital elevation model. My elevation model was a 30-meter resolution. That means we've got an average elevation over an area that's 30 by 30 meters wide. From that, I calculated slope, and slope looks at, for every processing cell, the 8 neighbors around it, and calculates the maximum slope from the neighborhood around each cell, and that's the cell value for slope. It's the maximum of the 8 surrounding cells. But these are 30-meter cells, and we're already starting with an average elevation. So we do have some degradation of reality here. We've got a maximum slope value representing the neighborhood around each cell, but we're talking about a fairly large area. So we do have some loss of fidelity and loss of accuracy. And I've got a square area representing something that might be happening that's more interesting on the ground than is being represented by one value for a 30-meter area, 30-meter squared area. Okay, to calculate the areas, let's say I need something that's around 1 acre. So I'm going to convert these to polygons so I can easily calculate the areas of these kind of low slope polygon areas. When we convert raster to polygon, we can simplify, which gets rid of the jagged stair-step edge and smooths it out a little bit. So here we are getting another degradation of accuracy and need to be suspicious of the amount of precision we're putting on these area calculations. But let's go ahead and do it in the attribute table, calculate the area of each one of these pink polygons. And I've done that here in square meters, and look at the precision that ARC gives you. It's saying that, for example, this polygon, if I can get cooperation, is about 17,488 square meters, 0.688345. So we're talking massively sub-meter resolution or precision here on this polygon that has gone through a resizing and a reshaping and is representing values that are averaged from a 30-meter elevation data set. So we have both a scale issue happening that's limiting our ability to be incredibly precise, and we have a process that's kind of eroding at the precision of our data. ARC doesn't care about that. It's going to give you this incredibly precise number. It's your job as a user to understand the limitations of your spatial data and to understand the limitations that are being kind of implied by the processes that you're doing to your map and to your data. And so I leave you with this, this first world meme. There just are so many significant digits, and it's your job to make the intelligent choices to represent your data and your process appropriately. And that's it. Thanks.